In this section, I'd like to explain the stability of linear systems. A linear system is expressed x prime equal ax. Critical point can be found by the derivative of x with respect to becomes 0. So from this equations, we could find out x sub c equals 0. Also, if you substitute x sub c into this equation, this becomes 0. So x prime equals 0. Okay, so especially if we consider two dependent variables of the x and y, then critical point in this system is x sub c and y sub c both equal to the 0. So origin corresponds to the critical point. Then we'd like to consider the stability of the critical point of the origin. To consider the stability, we need to find the solutions. To find the solutions, we need to solve the characteristic equations. So characteristic equation is expressed a minus lambda I, a determinant of a minus lambda I equals 0. Then determinant a minus lambda b c d minus lambda. So if you expand this equation, it becomes here. This is equal to tau. AD minus BC, we change the deltas. So equation becomes a lambda square minus tau lambda plus deltas. Then we solve this equation for lambdas is equal to the tau plus minus square root tau square minus 4 delta over 2. So this is a solution. So there are three possibilities. First case is both lambdas are real distinct eigenvalues. And the second case is a repeated real eigenvalues. And the third case is a complex eigenvalues. So we'd like to consider these three cases. The first case is a real distinct eigenvalues. So to have a real solutions, inside of the square root have to be the positive quantities. Tau square minus 4 delta should be the positive quantity. So this is tau square minus 4 delta is a positive quantity. Then general solutions expressed x equals c sub 1, k sub 1 is a eigenvectors times the exponential lambda sub 1 t plus c sub 2, k sub 2 is the other eigenvectors corresponding to the lambda sub 2s. So there are three possibilities: stable node, unstable node, and saddle point. In the first case is the exponential terms. Both exponential terms become the smaller and smaller. And finally is approaching to the origin. So this case is approaching to the origin. So we consider this case corresponding the stable critical point. When we have a lambda sub 1 and lambda sub 2, both becomes negative quantities. So if we draw the curve for the y equal lambda squares minus tau lambda plus deltas can be expressed lambda minus tau over 2 squares minus 4 tau square minus 4 delta over 4. Then both lambda sub 1 and lambda sub 2 is a negative quantities. So this corresponds to these situations. This is y and this is lambda. So lambda sub 1 and lambda sub 2 becomes less than 0. Then to have these curves, axis of the parabola is correspond to the tau over 2s. And then this minimum point, so minus tau square minus 4 deltas over 4. And also the point crossing the y-axis. If you substitute lambda equals 0, this corresponds to the tau. So to have these curves satisfy these three conditions. First one, the tau square minus 4 delta has to be the positive quantities. Then this is a positive quantities, so total this becomes a negative quantities. So minimum point is less than 0. The second condition is the axis have to be placed to the negative So tau over 2 have to be the negative. And the last one, delta, this delta have to be the positive quantity. When these conditions are satisfied, both lambda becomes the negative quantities, and the critical point becomes a stable critical point. The second case is both quantity becomes the positive quantities. Then the particle is moving away from the critical point of the origin, because exponential lambda sub 1t and the lambda sub 2t, exponential lambda sub 2t, both increasing with times. So in these situations, actually both quantity is a positive quantities. So lambda, y-axis, like this situation. This is delta, 0. This is tau over 2. Lambda sub 1 and lambda sub 2. So in this case, three conditions need to satisfy tau square minus 4 delta positive. And the axis is placed in the positive. And the delta also have to be the positive quantity. This is the condition for the positive eigenvalues. So from this part, you can find that tau is a negative, delta is positive. So this corresponds to these conditions. And then from here, tau is positive and delta is positive. So from here, we could find this condition. And the last case is one of the solution is a positive and the other one is a negative. So this situation, lambda. Why? To find this situation, we have this one. So this is lambda sub 1 and lambda sub 2. And this is a delta. To have these curves, actually the delta, we only need one condition. Delta have to be the negative quantities. So when the delta is a negative quantities, lambda sub 1 is a negative, lambda sub 2 is the positive quantity. So first term is decreasing with times, but second term is increasing with times. So if you place the particle is here, particle is moving close to the origins, but in the direction of the k sub 2 is increasing because of the lambda sub 2 is a positive quantity. Okay, we call that this point is a saddle point. It's an unstable critical point. Then I'd like to move to the next case of the repeated real eigenvalues. So in this case is a tau square minus 4 delta equals 0. So lambda have to be the tau over 2. So we have only single solutions of the characteristic equations. First case is two independent eigenvalues we could find. So in this situation, the k sub 1 and the k sub 2. Then lambda sub 1 in the case of the positive quantities. So this is equal to the tau is a positive quantities because the lambda tau over 2. So lambda is positive means that tau is a positive. Then if you place the particles here, amplitude is increasing because of the exponential lambda sub 1t. Particle is moving away from the origin. So we consider this situation is a unstable critical point. But sometimes we have a lambda sub 1 is a negative quantities. So this is correspond to tau is a negative. Even if you place the particle somewhere, it's approaching to the origin. So this case is a stable critical point. But in this case, we could find a single independent eigenvalues. So the solution, general solution is expressed the exponential lambda sub 1t, but second solution is t times exponential lambda sub 1t and the exponential lambda sub 1t. I explained how to find the eigenvector of the k sub 1, 1. To find the general solution, we need to find the second vector k sub 1, 2. So once we find the k sub 1, 1 and the k sub 1, 2, we can build the second solutions. And by combining the two solutions, we could build the general solutions. So in this case, the important point is that if the tau is a positive quantity, the critical point becomes unstable. If the tau is a negative quantity, critical point becomes a stable critical point. The last case is a complex eigenvalues. The characteristic solutions has a complex eigenvalues. So in this situation, tau squares minus 4 delta is a negative quantity. Then general solution is expressed this one. And the alpha is expressed tau over 2. And the beta is expressed square root 4 delta minus tau squares over 2. Then solution is expressed with these equations. By looking at these equations, you can easily find that the exponential alpha t becomes a really important quantity. Then alpha is a positive quantities or negative quantities. Distance from the origin is changing because of the exponential alpha t. So when the alpha is a negative quantities, the distance to the origin is decreasing. But due to the existence of the cosine terms and sine terms, it's spiraling into the origin. In this case, alpha is a negative quantities. This means tau is a negative quantities because alpha equals tau over 2. So if that alpha is a positive quantities, actually the particle is moving away from the origin. In that case, unstable critical point. When the alpha equals 0, so this corresponds to tau equals 0, then particle is moving around the critical point. So origin becomes a stable critical point. Okay, this is a summary of our finding. When the lambda sub 1 and lambda sub 2 both becomes a negative quantities, lambda sub 1 and lambda sub 2 is a negative quantity, it becomes a stable node. So in this case, the tau is a negative, delta is a positive quantities. When the lambda sub 1 and lambda sub 2 both positive quantities, lambda sub 1 and lambda sub 2 both positive quantities, then tau is positive, delta is positive, unstable node corresponds to these regions. When the lambda sub 1 is a negative quantity and the lambda sub 2 is a positive quantity, that corresponds to the saddle point. So lambda sub 1 is a negative, lambda sub 2 is a positive quantity. This corresponds to the saddle point. In this situation, is a delta is a negative quantities, corresponds to this region. When the repeated values, tau square minus 4 delta equals 0. So it corresponds to the on the curve. Lambda is a positive quantities. That corresponds to tau is a positive quantities. This on this line is unstable. And then the other side is lambda is a negative quantities. On this line is stable. When the complex eigenvalues, tau square minus 4 delta is a negative quantities. When the alpha equals 0, so tau equals 0. That corresponds to the centers. So on this axis. When the alpha is a negative quantities, so this means that tau is a negative quantity. It corresponds to the stable spiral. The last one is tau is a positive quantities. So it corresponds to alpha is a positive quantities. Is an unstable spiral. So when you discuss the stabilities of the critical point, always it's better to look at these figures. You can easily find out the stability of a critical point. Okay, this is the end of this session.